Hey guys, this is 18.2, Strengths of Acid and Bases. When you finish watching today's video, you should be able to compare strong acids and weak acids, strong bases and weak bases. You should know, when you have a strong acid, what the conjugate base is considered, and you should know how to write a Ka and a Kb for your acids and bases. Strong acids are considered strong because they ionize completely when they go into those solutions. They are also good conductors of electricity. When we say they ionize completely, what we're talking about, if this was hydrogen and chlorine, we would say that this was hydrochloric acid. When it goes into water, the hydrogen would split apart from the chlorine and they would both float separately. Now the hydrogen would be a positive ion and the chlorine would be a negative ion. When we put strong acids like HCl into water, they ionize completely, meaning that every single one of the HCl ions are going to split apart into positive hydrogen and negative chlorine. Because they completely separate in a reaction, you don't have, like other acids, the reverse reaction occurring. So there's not going to be a part where the chlorine and the hydrogen actually recombine together to make hydrogen chloride again. So it's a one-way arrow, and so you only use a single arrow, not a double arrow. Now, when we talk about strong acids, we always say that the conjugate base is weak. And when we say that the conjugate base is weak, we're talking about, for instance, HCl, when it broke apart, as soon as the hydrogen was given away, this is the acid because it can donate a hydrogen, this is now my conjugate base, the chlorine. So when we say this, we mean that the chlorine is not strong enough to steal the hydrogen back. So if you remember, that little hydrogen, this is a water molecule, the little hydrogen floated around until it bonded with a chlorine and became hydronium, right? And this is not strong enough to steal the hydrogen back from the hydronium. So this is considered a weak base because it is unable to take back the hydrogen from the hydronium ion. And that's always the case. When you have a strong acid, its conjugate base will be weak. If you have a strong base, the conjugate acid will be weak as well. Now, when we talk about a weak acid, they're only going to partially separate in aqueous solutions. Because they don't ionize completely, they're considered poor conductors of electricity. That means that there's less, when they split apart, there's less ions available to move and to conduct an electric current. So they're actually weaker conductors of electricity. When we have this, because we have some of them splitting apart, the acid and base, conjugate acid and conjugate base, actually will reform together to make the acid and the base from the original side of the arrow. So this means that it is a double reaction. We have a forward reaction where you have something splitting apart, and a reverse reaction where they're combining back together to make the original ingredients. So because of that, we will represent weak acids and weak bases with double arrows. Here's an illustration demonstrating this. So notice how your strong acid, you have all of the acids splitting apart into hydronium and the corresponding base. In the weak acid, you still have many of the acid still together in their original form. So notice that they have not ionized completely. Now, because we are working with these, and in a weak acid and a weak base, we have a double arrow, we can write an ionization constant expression. Remember in the last chapter where we wrote our KEQs, or our equilibrium constant expressions, we are able to do that with acids and bases as well. So when we write this, the acid ionization constant expression is going to be represented as a big K again, but instead of a little subscript as an EQ for equilibrium, we're going to have to specialize this one as acids. So we put a small a as our subscript. So this is the Ka. This is the value of the equilibrium constant expression for the ionization of a weak acid. And this is exactly the same process that we went through when we wrote our original K values. Remember, we put the product over the reactant, put them in brackets so that we have their molar concentrations, and we raise them to the exponent that was the same as the coefficient. Now this is even easier though, because in these equations our coefficients are always 1. And so we don't even have to worry about writing the power because the power is always going to be to the first power. And if you raise something to the first power, it is itself. So you don't even have to write those exponents this time. Now, remember, in our k values, the only things that cannot be shown are are solids and liquids. So we're going to continue that right now, and we're never going to include a pure solid or a pure liquid in our k value. Now, we are introducing the new term aqueous with the k values, and aqueous, just like a gas, will be included in the k values. So we are going to include aqueous, but again, not the solids or the liquids. So notice how you have this equation and you put your reactants on the top, the A negative and the H3O positive, and we put on the bottom the HA, but we left out the H2O because that's a pure liquid. Strong bases are exactly the same thing. They will dissociate completely into metal ions and hydroxide ions. Our weak bases only partially separate again. And again, with our Kb, this is the same idea, only when we're doing this, it's for the base, and so our Kb is the value of the equilibrium constant expression for the ionization of a base. Notice that the smaller the Ka or the smaller the Kb, the weaker the base or the acid is going to be. And notice again, you have the products over the reactants, and they're each raised to the power of 1. Don't include the pure liquid water. All right, I have a few examples on the board, and then we're going to be done with this. So we start with this CH3COOH, which is aqueous and is combining with water. And in this example, we're going to have this for a Ka, so we're looking for the acid. And that means that this is my acid. And that's important because it determines what the water is going to do. So if this is my acid, it's the one that's donating a hydrogen. And it's going to donate this hydrogen on the end that's all alone. So when we have this, the hydrogen comes and it goes and joins my water to form H3O, which is no longer considered a liquid because now it's dissolved in water, which means it's aqueous. It is also positive because it gained a hydrogen. Now this, without that hydrogen there, is actually CH3COO. And notice that it got a negative charge because it lost a hydrogen, so now it is negative. Now, the Ka, it's pretty easy. We're going to take our products and we're going to divide them by our reactants, but not including our pure liquids. So we're going to put in brackets our H3O, and remember to include the charge. Notice that this does not have an exponent because this is already balanced, and we're going to multiply it by the value of the CH3COO negative. We're going to put this all over our reactant that gets to be included, which is the CH3COOH. And that's all we have to do. Now, if they give you concentrations for these, molar concentrations, you might have to multiply and then divide to solve for your original K. But that's all. All right. And the last example is our base. So we're going to find the Kb. And what we're going to do is, again, this is going to be my acid in this situation since this one's my base. And so this one's going to donate the hydrogen and become OH. And that hydrogen goes over here. Now look, if you don't know where to put the hydrogen, you can always stick it on the front. But if you have a poly that's common, like NH2 can become NH3, which is a common poly, you need to put that poly in there. So this is going to become C6H5NH3 aqueous. And again, you put your products. Over your reactants. And that's how you write your Ka and your Kb.